You already know scalar fields, one number at every point in space. Picture walking around a room where every spot has a temperature reading. That's a scalar field. Now picture something different. At every spot, instead of a number, there's an arrow pointing somewhere with some length. That's a vector field. So scalar field gives you a number at each point. Vector field gives you an arrow at each point. Physical examples of vector fields include wind speed and direction or the pull of a magnet. To sketch one, pick several sample points and at each one draw an arrow. The direction comes from the field's formula and the length shows how strong it is there. Take the example field F equals negative y I hat plus x j hat. At every point the arrow points sideways, perpendicular to the line from the origin to that point, creating a spinning, swirling pattern like a whirlpool. Now, here's something you already know, wearing a new hat. The gradient of a scalar field is itself a vector field. Standing on the landscape described by that scalar field, the gradient arrow always points in the steepest uphill direction, right at that exact spot. The pattern to recognize. Gradient of f means take the partial derivative with respect to each variable and stack them into a vector, so grad f equals curly df by curly dx I hat plus curly df by curly dy j hat plus curly df by curly dz k hat. Let's make this concrete with a worked example. Task: find the gradient vector field for f equals 2xy plus z squared y. Step 1. Find curly df by curly dx. Freeze y and z and differentiate. The 2xy term gives 2y, and the z squared y term has no x in it at all, so it vanishes completely, giving curly df by curly dx equals 2y. Step 2. Find curly df by curly dy. Freeze x and z. The 2xy term differentiates to 2x, and the z squared y term differentiates to z squared, since z squared is treated as a constant multiplier. So curly df by curly dy equals 2x plus z squared. Step 3. Find curly df by curly dz. Freeze x and y. The 2xy term has no z in it, so it vanishes, and the z squared y term differentiates to 2zy. So curly df by curly dz equals 2zy. Step 4. Stack the three results into one vector. The gradient of f equals 2i I hat plus the quantity 2x plus z squared j hat plus 2zy k hat. That's the final answer. Now for a key visual fact that ties back to how we sketch these fields. Picture a contour map, like on a hiking map, with lines showing constant height, and now picture the gradient arrows drawn on that same map. Every single gradient arrow crosses the contour lines at a perfect right angle. This is because contour lines show where the function isn't changing, while the gradient shows the direction of fastest increase, and these two directions are always perpendicular, everywhere, without exception.